This here is ordinary matter, and this here is dark matter. No, don't worry. I didn't forget to add images. Dark matter is invisible. That means you cannot see dark matter. But dark matter makes up about 25% of the entire universe. The matter you can actually see accounts for only about 5%. Now you'll ask, 100 minus 25 plus 5. So what makes up the remaining 70% of the universe? That 70% comes from dark energy. In other words, dark matter and dark energy together comprise 95% of the universe, yet we can't directly observe them. Before we dive further into this discussion, please like the video and subscribe to the channel. First, let's talk about dark matter. You already know what matter is. You learned about it in childhood. The 4 states: solid, liquid, gas, and plasma. Anything you can see around you is one of those. And dark means hidden or mysterious. So dark matter is equally mysterious to scientists. That's why it's called dark. But don't think dark matter literally lives in darkness. It's just a metaphor. You might wonder, if we can't see dark matter, how do we know it exists? We can't see dark matter itself, but we can observe its effects. A cluster is made up of many galaxies, and each galaxy contains hundreds of billions of stars, countless planets, moons, and enormous gas clouds. For instance, our Sun is one star in the Milky Way galaxy. Most galaxies also host a supermassive black hole at their centers. All the stars, planets, moons, everything revolves around that black hole. When any object orbits a central point, a pseudo-force called the centrifugal force pushes it outward, trying to fling it away from the center. Obviously, galaxies aren't flying apart, so something must hold them together. That thing is gravity. The total mass of all the stars, planets, moons, everything in a galaxy generates its own gravitational field. The more mass there is, the stronger the gravitational pull. Gravity balances the outward centrifugal force, keeping galaxies intact. The first hint of dark matter came in 1933, when Swiss-American astronomer Fritz Zwicky studied the Coma Cluster in detail. Before Zwicky, scientists thought stars in galaxies moved fairly slowly. No one knew, but they realized it must be some kind of matter unlike anything in the standard model, matter that neither emits nor absorbs light, so we cannot see it, yet still produces gravity. They named it dark matter. Remarkably, we still have never directly detected dark matter, but it fits our theories perfectly, and we've observed its influence many times, such as in galaxy rotation curves and gravitational lensing. So, what do we actually know about dark matter? 3 things. First, something definitely exists. 100% there's something out there. Second, whatever it is, it interacts via gravity. And third, there's a lot of it. If you are still here, please like the video and subscribe to the channel to get science content like this every week. Alright, dark matter's done. Let's move on to dark energy. Like dark matter, scientists have never directly measured or detected dark energy, but we've seen its effects clearly. How did we find it? In 1929, Edwin Hubble, after whom the Hubble telescope is named, used the most powerful telescope of his time to look at distant galaxies. He discovered that their light was redshifted. Redshift means that if a distant galaxy is moving away from us, its light stretches to longer wavelengths, appearing redder. Conversely, if it were moving toward us, it would be blue-shifted, shorter wavelengths. This shift is called the relativistic Doppler shift and comes straight from Einstein's theory of special relativity. Hubble saw that essentially every distant galaxy was redshifted, meaning galaxies are all moving away from each other and the universe is expanding. Until about 1998, astronomers debated how this expansion would proceed. One theory said that the universe's total mass and the gravity it generates would let it expand forever, but ever more slowly. The other theory said that gravity would eventually halt the expansion at some maximum size. But in 1998, studies of many supernovae showed a surprise. It's accelerating. Its expansion rate is speeding up over time. What causes this acceleration? That's how we know about dark energy. As the universe expands, space-time itself stretches. Some astrophysicists even say you can't separate space-time from dark energy. Just like Einstein's E equals mc squared tells us energy and mass are interchangeable. Space-time and dark energy may be 2 sides of the same coin. That's why, as space-time expands, dark energy's density remains constant and uniform. NASA's Nancy Grace Roman Space Telescope, slated for completion by 2027, will probe faraway exoplanets and study dark matter and dark energy in unprecedented detail. In short, dark matter and dark energy challenge our understanding of the universe. They expose the limitations of our current physics, especially gravity. Scientists are working to unify general relativity and quantum mechanics. If they succeed, we may no longer need dark components to explain the cosmos. But that day is still far off. And that's what makes science exciting. There's always more to discover. Since I alone run this channel, it takes me a lot of time and effort to make these videos. So if you like them, or at least appreciate the effort, please like the video and subscribe to the channel. It means a lot to me. Also, if you'd like to see a video on any other topic, let me know in the comments. Thank you. Also, if you are interested in knowing why different animals have the same patterns on their skin and how math can answer that, then you should check out this video by clicking on the I button.